So here we have another example of solving a differential equation that's first order, first degree, and this equation will, as we'll see, lends itself to the separation of variables approach, which, speaking of that, we recall that when we have an equation of the form of some function of x times y dx and then some function of x function y dy, then we can usually, by inspection, find an integration factor, pulling one of the functions of x and one of the functions of y, such that when we multiply our original equation through by this factor, we end up with an equation of this form. And this form is important because you see the first term is all in x, the second term is all in y, and so this is what's meant by separation of variables. So our equation, we can do some algebraic rearranging, which is really just cross multiplying, and we arrive at this. And so now we can see that this is in the general form that we're looking for separation of variables. We have function of x and y dy, function of x, which is just a constant, y dx. So from this equation, we can assign these secondary functions that we're going to use to create our integrating factor. So in this case, it's just x and y, so it'll be 1 over x and y. So when we multiply through our original equation by this integrating factor, we see we come up with this equation. And this is the form that we're really wanting, right? So now we have our function just in x, our function just in y dy. So this should be solvable using separation of variables. So here we can continue to simplify this by separating the y term into separate fractions. And so when we do that, gets us to this next equation, which this is much more conducive to doing integration by terms, which we'll see on the next slide. So here now we can just apply integration. So the first term is just in terms of x, second term in terms of y, and then we also, just for completeness, show integrating the 0 because that will result in some constant that we need to keep track of. So performing these integrations directly, most of these will turn into just natural log integrations with, of course, the 1 just integrating to y. And then we can take advantage of some natural log properties and some other algebraic cleanup and simplify this a little bit more. So here, taking that equation, again, combining terms and utilizing natural log properties, we come to this. And now if we simply just take the exponential of each side of this equation, that gets rid of the natural log and gets us to our final answer, which we're presenting as the solution to the differential equation above, is this equation here.